Okay, so let's continue our discussion, and the goal is to identify what exactly this blob is. Okay, we already have an idea what this is. This looks like all these factors. Okay, but we want to give a precise expression for this. So what I've done is I've pulled out two sheets from my previous course, the first course on quantum field theory, and here let's see what the way we had written down the Feynman rules for n-point Green's function. Okay, so here you have Gn x1 to xn, and here this is J tilde. So that's the Fourier transform, where doing a Fourier transform involves multiplying with these exponential factors e to the minus I pi xi. Okay, so there's the Fourier transform. So I'm calling this particular diagram as f. Okay, and the Fourier transform being f tilde. This is a 4-point function, and you see you have these d4 xi to the minus I pi dot xi, because we are doing a Fourier transform, times the Feynman diagram in the coordinate space using momentum space Feynman rules. So recall what we studied at that time, that you label each propagator by some momentum ki. Okay, in this case you have 6, so you have to integrate over all the 6, and at each external point you include a factor e to the minus I times the momentum that enters into that external vertex times xi. So here minus k1 is entering into x1, so that's why you have e to the plus I k1 x1, okay, because the sign gets reversed. And then you have propagators, then delta function, momentum conserving delta function at each vertex, and then all these factors. Okay, and let's see what happens then. So if you take this exponential coming from Fourier transform and that exponential coming from the Feynman rule for g in x coordinates, you get a delta function 2 pi to the 4 delta 4 pi minus ki. Okay, and then further manipulating this and doing all the integrals. Let's say we do the integral over k6. Okay, we still keep the integral k5, this one. Okay, you have k5 and k6 running in the loop, and I should have only one loop momentum left because this is a one loop diagram. So I do the k5 integral, that's trivial, and I am left with a apart from these propagators and this loop momentum and other propagators, I am left with a overall momentum conserving delta function times 2 pi to the 4. So you can integrate over k5 also. That's not so easy, but you can. But here we are just integrating over all those momenta which are easy to integrate because of the delta function. Okay, so that's why I integrated over k6. So the thing that we should carry from here is that I get at the end a 2 pi to the 4 times a delta function, and delta function involves all these momenta. In this case, because we were looking at a 4-point function, I get sum of all these 4 momenta. Okay, that's what we should remember from here, and also the Feynman, the way this is written, the Feynman rules. Okay, so now we will utilize this, and let's revert to our original thing. So here I have let's look at only one leg. Okay, and each leg for each leg you'll have similar thing, but I will not worry about it now, but I will draw it nevertheless. Okay, we are trying to interpret or find out what exactly we have multiplying G amputated or G tilde amputated. Okay, what are the exact factors that multiply? In generic terms, we know exactly in terms of propagators and all this, but generically what is that object? So let's concentrate only on this one. So here is the Fourier transform, integral d4 x1 e to the minus I q1 dot x1. Okay, this factor is coming because I am looking at a Fourier transform, because I am looking at G tilde q1, q2 and so forth. Okay, and I will write only for leg 1, and this is right now drawn in the coordinate space. I mean, this is G tilde x1, x2 and so forth. Okay, then if I write the expression of this G tilde x1, x2, x3, xn, then it will be, you remember, yeah, so here I should assign momenta k1. Okay, I will not worry about these, but let me nevertheless write. Okay, and this one let me call k1 prime. Okay, I'll put the arrow this way. Okay, so that's Fourier transform of this object. You have d4 k1 over 2 pi to the 4, then e to the I k1 dot x1 or k1 prime dot x1. Okay, this is exactly this factor. Okay, you see, coming from here. So that's this factor. Then I should write all the propagators. So I have I over k1 prime square plus, minus m square plus I epsilon. Okay, remember here it is not the physical mass, here it is the bare mass that appears in the Lagrangian, times all those things that are contained in the blob. Okay, all those contributions coming from there. So I'll just denote it like this, which I will write as f of k1. So this object is f of k1. Okay, and it will depend only on this momentum k1, because that's what enters in here, and all other momenta that you will have inside, they will be dummy, they will be integrated over. Okay, and because of the momentum conservation at each vertex, the only momentum that will, on which this object will depend on, will be k1. So that's why I write f of k1 or yeah, f of k1 is fine, times you have integral d4 k1 prime 2 pi 4 I over k1 prime square minus m square plus I epsilon. Okay, times 2 pi to the 4 delta 4 k1 minus k1 prime. Okay, why do you get this? You get this because of momentum conservation at each vertex. Okay, so that momentum conservation will ensure that k1 is equal to k1 prime, and that's why you are going to get this factor when you write down the expression for this. Okay, once you have integrated out over all the other delta functions arising from the vertices inside this blob, you will end up with only one delta function, which will be k1 minus k1 prime, and then times all the remaining things which arise from the remaining parts of this this diagram or sum of diagrams. Okay, so I'll just write remaining parts. Okay, I'm writing diagram a bit loosely because you have to actually add up all the diagrams. So it is not just a diagram, but rather sum of all the diagrams. Okay, now this is G tilde basically. This D tilde okay. So what do you get? You collect x1 and integrate over it, and that gives you 2 pi to the 4 delta 4 q1 q1. Okay, there's some, I have made slight mistake. This is not k1 prime, this is k1 here. q1 minus k1. Okay, that's correct, times. Now if you let me change. This is not right way. I should write integral d4k1 over 2 pi to the 4. Okay, and then integrating over x1 gives me this delta function which I was telling, q1 minus k1, okay, times this should also have been k1. Now k1 is q1, so I can just write, because of the delta function, I can write q1 square minus m square plus I epsilon times f of, you can write as q1 times this integral. Just a second. Okay, times integral d4k1 prime k1 prime square minus m square plus I epsilon, and actually I can see there is a delta function here which says k1 prime, which puts k1 prime equal to k1. So if I integrate over k1 prime, I will get this expression with k1 prime replaced by k1, and this delta function 2 pi 4 will cancel with this, and this integral will be done, it will be taken care of. So I will just do that, but also because of this delta function k1 is forced to q1, so eventually this k1 prime get replaced to first k1 because of this delta function, and then eventually to q1 because of this delta function. So let me just remove this and write, I'll just remove all this and write I over q1 square minus m square plus I epsilon times remaining parts of the diagram. Okay, and I should also remove this. I have done integral over k1 as well. So this is gone. sorry, this entire thing is gone. Okay, this is correct. So this is the previous expression is equal to this. So you can also check this way that what I am writing is correct. You have one delta function here, okay, and one delta function coming from doing x1 integral over these two exponentials. So at the end I am left with two delta functions and integrals over and two integrals d4k1 and d4k1 prime. So when I do those integrals over two delta function, neither I should have those integrals left nor the delta functions, okay, and that is why you have this result. So this is fine, no problem here. I should also again, this is, I will be drawing like this, okay. Good. Now this is something we already have seen, but now I want to recall that the general expression of G tilde which we saw here. Okay. So if instead of this 4-point function, if I was looking at a 2-point function, like, okay, how do I get white color? Here. So if I look at, instead of this 4-point function, if I look at 2-point function, okay, sorry, any diagram which contributes to 2-point function, then if you repeat the same steps, then at the end you will have all these propagators, okay, so in this case 2 propagators, and then apart from other things you will have a 2 pi to the 4 delta 4 q1 plus q2, okay. So this, if I call this as q1 and this as q2, then this will have, in addition to other factors, in addition to the propagators and other factors, will have delta 4 q1 plus q2, okay. That's what you are going to get, and that is what I want to utilize now. Okay, how do I get rid of this? Okay, so as you can see, as I just said, delta G tilde of q1 q2, okay, which is just the Fourier transform of 2 points Green function, will have, as we have seen above, I over q1 square minus m square plus I epsilon times this f of q1, okay, all those things which come from here, from this blob, all the internal vertices and internal propagators, times again you get I over q1 square minus m square plus I epsilon, and then at the end you have 2 pi to the 4 delta 4 q1 plus q2. Okay, I will denote this factor as G tilde of q1. Okay, my G is looking strange. G tilde of q1. So this becomes G tilde of q1 times 2 pi to the 4 delta 4 q1 plus q2. Okay. Now you see that here we had exactly this when I analyzed the general thing. So contribution from the leg 1 was I over this propagator times fq1 times again the same propagator multiplying the remaining parts of the diagram. Okay, and here what do you have? If you look at the 2-point function, then it has exactly the same form. Okay, this propagator with q1 momentum in it, then fq1 which is exactly the same fq1. Okay, then again this propagator, but another factor of 2 pi to the 4 delta 4 q1 plus q2. Okay, so you see that what appears here, this piece, this is g tilde of q1. So I will write this as g tilde of q1 times remaining part of the diagram. Okay, and if you do the same on each of the legs, then you get g tilde q1 times g tilde q2 and so forth, so and so forth up to g tilde qn times what? Times exactly what we call as g tilde amputated. G tilde amputated Green's function with all these momenta. Okay, so that's what we have achieved, and I know what exactly g tilde n is. G tilde, I should put a superscript 2. That's g tilde 2. And what is g tilde 2? This is exactly this object. Okay. Now I will show you that g tilde 2 here with only one argument q1 is basically a Fourier transform of Green's function g tilde 2 x1 x2, but involving only one variable, that is or instead of q1 I will just write q, okay, because I am doing it in general. So g tilde 2 x prime is I'm doing a Fourier transform but with only one variable. Okay, so this is what defines g tilde 2 of, I could write, okay, that's fine. Okay, now also if you look at the Fourier transform involving both the variables, transforming both x and x prime, then it was defined to be g d4x prime e to the minus I q dot x e to the minus I q dot x prime, okay, times g of x1 x2, but that I will substitute from here. So instead of g tilde 2 x1 x prime, I will just substitute this. So this is integral d4k 2 pi to the 4 e to the I k dot x into e to the minus I k dot x prime times g tilde 2 of k. Okay, let's do x integral. So this piece involves the x, that piece involves x. So that gives you and similarly for x prime you'll again get a delta function just like for x, and then you're left with integral d4k. So you'll be left with d4k over 2 pi to the 4, okay, times g tilde 2k times these delta functions that you get after doing x integrals. So you get 2 pi to the 4 delta 4, this one and this one gives q minus k, and x prime integrals give q plus k. something wrong. Some primes are missing. Sorry, here should have been a prime. Okay, so this one is fine, and that one should be q prime minus k. Now, so, no, there is something wrong. Q dot x, k dot x. So there is a relative sign. So fine. Here k minus q prime. So it should be a plus. Okay. Now let's do the integral over k and utilize this delta function. 2 pi 4 cancels here and there, and you get g tilde 2 k. Okay, sorry, not k, because k should be forced to become q. So g tilde 2 of q, and this should give 2 pi to the 4 delta 4 q plus q prime. Okay, so what we see is that the Fourier transform of this Green's function, or g tilde 2 q prime, that is just g tilde 2 q with one variable times a overall momentum conserving delta function. Okay, and remember here you get a q plus q prime, because the way we have been doing is, if this is q and that is q prime, then you get q plus q prime. Okay, and remember we had at the external vertices, okay, we had the momenta always assigned either entering from all the sides or exiting on all the sides. That's why you get a delta 4 q plus q prime. Okay, so now we have an understanding of what that factor g tilde 2 q is. Why? Because you see here, this entire factor is same as what appears in here. Okay, so clearly this factor times the delta function is g tilde 2 with q1 q2. That is something we argued. Okay, we argued some time back that 2-point function, if you take the Fourier transform, then it is 2 pi overall momentum conserving delta function times g tilde 2 of q1, where this is this object, which is what appeared in the previous expression here. Okay, and now we have an interpretation for this factor. What is that? That this is, so if you were to take a 2-point function in the Fourier space, then that will be equal to 2 pi 4 times delta 4 this, and the prefactor is what enters into here, into this, in this. Okay. Okay, good. So this is what I wanted to show, and then we are almost there. I will make some connection. I will make a connection of this with the scattering amplitude. I will define it, and then we will proceed from there.